Welcome to Chapter 6, lecture. Chapter 6. Chapter 6 serves as sort of an introduction to a lot of reactions. Okay, so the chapter starts off with a sort of a fundamental question. Why do certain reactions occur when two compounds are mixed together, whereas others do not? To answer this question, we must learn how and why organic compounds react. And then it goes on to say reactions are at the heart of organic chemistry. We've already hinted at this. We introduced reactivity quite early because we want to get you thinking about these principles sooner rather than later. And it says there's a few basic themes. I can't stress enough how important these few basic themes are. There actually aren't that many basic themes, but they are combined in complicated ways, and that is what makes it difficult. So if you seek to memorize all these things, all these reactions, you're going to be overwhelmed. Whereas if you learn the basic themes and really learn them, then you'll be able to understand and work through these reactions. It'll still be difficult, but manageable. Okay, manageable with a lot of time still put in. So 6.1, I recommend reading. Strongly recommend that. It just gives some information, okay, as to how we write reactions and things like that. I'm not going to write all that out in the lecture. We'll do things slightly out of order. We'll do section 6.3 here first. And section 6.3 is entitled Bond Breaking and Making. Okay, so I'm going to look at both of these principles, how bonds break and how they make. Okay, so when we look at organic reactions, sometimes you'll see me do RX and S for organic reactions. There's two. We're gonna categorize things in different ways. Okay, there's a few different ways to make categories, but in terms of organic reactions, there are what we call concerted and stepwise. Are single-step reactions. The whole reaction sort of happens at once. Okay, we're gonna explain some of these more, but you go straight from starting material to product. A certain amount of energy is required for this in all cases, but you just go straight there. There's no intermediates. The term intermediate will be an important one. We'll talk about it a lot. Stepwise are much more common. It's multiple steps. It could be 2 steps, 3 steps, etc. But you go starting material to INT, intermediate, to product. Some intermediate that exists for some finite lifetime, as opposed to a transition state, which we'll talk about. Another way we can break these divide reactions is in terms of bond breaking. Okay, so in terms of bond breaking, we can break this into 2 categories. We call this homolysis, homolysis, or heterolysis. Okay, another word that we use is homolytic cleavage and heterolytic cleavage. Cleaving a bond means breaking it. Okay, and what we mean here is homolysis. We break this in a uniform way. So all these bonds, right, are 2-electron bonds. And homolytic bond cleavage means that bond is being ripped apart and 1 electron is going with both A and B. So you get radicals. We won't talk about radicals very much. We put the electron over here. Okay, those 2 electrons are now split, and this is a radical reaction. We'll talk about this in chapter 15, but we will get back to it this semester, but we won't really talk about it much more until chapter 15. We might mention it again in this chapter. But we use what we call fishhook arrows. Fishhook arrows, and that's sort of a half an arrowhead. Okay, so a full arrowhead means 2 electrons. And let me illustrate heterolysis on the next slide. We can have, I'll draw it nice and big because this is by far more common. Now A and B, the electrons can go with A or B. So here we're going to show the A pathway where the electrons are going. This is pathway A, right? A is getting the electrons. B is then a cation left behind. So the bond is breaking heterolytically, non-uniformly. Whereas B, notice the full arrow, pathway B, B is getting the electrons. We have A plus and B minus. Okay. This is much more common. We use full arrows. Full arrows indicate two electron movement. Okay. So along the lines of bond breaking, let's look at some common intermediates. Let's look at the radical. We showed it in general terms of A and B. Let's look at the radical version of carbon. Okay, so we can look at something like this. We're using Z to represent some kind of leaving group. Okay, we'll talk about leaving groups a lot in chapter 7. But it's going to leave. Here we're going to show it leaving in a radical sense, homolytic bond cleavage, half arrow, like so. This gives a radical. And another radical. Okay. Think of charge conservation, think of electron conservation. If you had two electrons in the bond, you've got to account for both those electrons. So now there's a single electron pair. This is called a radical. In the past, I've taught this where I jumped to chapter 15 right away after chapter 6. In some sense, it's easier to wrap your mind around. You just heat these things and bonds break. When you heat up organic molecules, bonds break. But now I teach it in order of the book. Chapter 15 is later. So what you get is a radical. The way we look at this radical is similar to a carbocation, which we'll get to in a second. We have a p orbital. There's a lot of complications to this. We say this is sp2 hybridized. Okay, it's a single electron. It's actually kind of probably passing from each lobe in the p orbital and transitioning from sp2 to sp3. It's complicated, but we say it's sp2, and there's a single electron in the p orbital, so it's not an empty p orbital. But this is neutral. Okay, neutral but electron deficient. Again, this is probably the last we'll say about radicals. Okay, for now. So not a major focus. Don't stress out about radicals right now, understanding all of them. We'll come back to that at the very end of the course, of this course in chapter 15. However, let's look at heterolytic again now with carbon. We got this Z. And there's two possibilities. Let's be consistent. Pathway A, so to speak, and pathway B. We went from left to right. If pathway A is the electrons going to carbon, then we're going to get a carbanion. And a Z plus. Okay. And if we drew this in 3 dimensions, it would be sp3. Now the difference, if you want to think about it in somewhat simplistic terms, is a lone pair counts as a group, so therefore it's tetrahedral. A single electron does not count as a group, so therefore it's not tetrahedral. It's sp2, trigonoplanar. This is electron rich. It's a carbanion. We'll talk about these less so than the next intermediate. There you go, carbanion, okay, sp3. That's heterolytic, but if Z is more electronegative than carbon, which is what we're going to see in chapter 7, this is not going to happen. Okay, pathway B will happen, where the electrons go towards the more electronegative atom, generating a carbocation. And this intermediate is by far the most important intermediate we will see. We'll see carbocations in chapter 7, chapter 8, chapter 9, chapter 10, chapter 11, so on and so forth. We'll probably see carbocations in almost every chapter. So the carbocation and the Z group has a negative charge. Again, charge conservation. If you break this bond, you started with a neutral system up here. You got to have a net neutral system, plus, minus. What's the carbocation look like? We've mentioned this a little bit. An empty orbital with a plus charge on carbon, the formal charge sp2, empty p orbital. Very electron deficient. Carbocation, carbocation, carbocation. Can't stress enough how important these are, so you want to understand something about these, okay? So if bond breaking can be homolytic or heterolytic, bond formation can be the same. Quickly, bond formation looks like this. Homolysis, radicals can recombine. And again, there's a lot of driving forces. We'll talk about these: kinetics, thermodynamics, why bonds break, why bonds form. Okay, so just in general terms, you could have A plus, B minus, and the opposite. This can attack. This is what we'll see a lot of. Okay, we'll see negatives attacking positives to form new bonds. Okay. Lewis base attacking a Lewis acid. Very, 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 very important. So bond breaking, bond forming. So let's go over reaction types. Again, that's the 30,000-foot view, so to speak. Let's go a little lower and look at a little bit more specific, but still very general. Reaction types. There's 3 basic types. And this is, again, what I mean by basic themes. Bonds can break, bonds can form. They can break and form homolytically or heterolytically. They can be concerted, they can be stepwise, okay? Now there's a different way to categorize reaction types. There's 3 basic reaction types. Think about that. As you go forward, the number of reactions you're going to see, at least overall they can fit into these steps, and the intermediates can fit into these steps. Okay, 3 basic reactions. So what are they? One is substitution. Okay, we're going to talk about the opposite reactions for each of these. The opposite of substitution is substitution. You'll see what I mean here in a second. You got a carbon Z bond. Again, we're going to refer to Z as a leaving group. Okay, you're going to see a nucleophile, and all this means is a Lewis base that's attacking carbon. We're not talking about mechanism, about how this happens yet, but we're going to replace the Z, right? The Z group is going to get replaced by the nucleophile. Substitution. That part is very straightforward. The how is not as straightforward, okay? But substitution. And again, remember, in principle, this reaction can go in the opposite sense. Okay, there's other types of substitutions, but this is an intro substitution, okay? So number 2, elimination. We're going to talk about substitution and elimination in chapter 7. Chapter 7 and 8, okay? So, elimination, what's it look like? Carbon. Now we've got an X and a Y, okay? Again, these are very general, and truth be told, Y is Z. You're going to have a leaving group, okay? Z does not just mean a leaving group. We're just using letters to try to give you a picture. So, but these sigma bonds are going to be broken. We're going to add a reagent. RGT is short for reagent, and we're going to form a double bond. Carbon, carbon, double bond. I'm going to draw it in a funny way. That's not actually the geometry, but just so you can see it. And what do you have? You have X and Y forming a new bond, and you get a new pi bond. Okay, so you form double bonds here, and you can form triple bonds, but you eliminate a molecule of XY. Okay? So by elimination, we get pi bonds. The opposite of elimination is addition. So if 1 and 2, substitution and elimination, are chapters 7, 8, and 9, addition reactions are chapter 10, 11. Okay? And what we see here is we see pi bonds, that's the right way to draw it. With a reagent now, we're going to add. This pi bond is broken. We're going to add this reagent, and it's going to add across the double bond. Generating 2 new sigma bonds. So it's the exact opposite. Elimination and addition are opposites. So a couple examples, just briefly. See things like carbon iodide bonds get broken. Things like sodium hydroxide, which you're familiar with, will be a nucleophile. Chapter 7, we'll see this a lot. Okay, we're going to see arrow pushing like this. The O, in this case, the OH minus is coming in attacking, kicking out the I, and you get, and you've substituted. You broke a CI bond and you formed a CO bond. It's the byproduct, sodium iodide. Okay. Again, we're going to go through this systematically in terms of mechanism. You could also have a CI bond and have more going on. And now what you're going to do under similar conditions, and I want to stress this now, I'm showing you the exact same reagent with a very similar alkyl iodide. And this is probably actually not going to happen, but I want to introduce it now to stress that we're going to learn how to tell the difference between certain reactions. This would probably still substitute. In fact, it would, okay? But to give you an idea, let's put a CH3 here and a CH3 here, and that bulks up this carbon. Again, I'm planting a seed for chapter 8. This bulks up the carbon, and now elimination will occur, and you'll get carbon-carbon CH3. So more important than anything now is to just sort of be listening and seeing what we mean by this. Okay, so what do you generate here? Sodium iodide and water. Okay, so now just big picture, you're going to see similar things giving different reactions under different conditions. Again, I can't stress that as enough. The conditions matter a lot. Okay, we're going to learn about the beginning material and the products, and then the reagents are going to matter a lot. Okay, and just to give you one more example of an addition reaction, you can take alkene, take the simplest alkene here, and add, let's do HI, just to be consistent with iodine now. And what did we do? We formed a carbon-hydrogen bond and a carbon-iodine bond on separate carbons. Okay. These two bonds are new. We broke this bond, broke a pi bond, formed a sigma. Okay, this is, again, chapter 10 and 11. All right, there's more, but let's move on to 6.4, bond dissociation energy. Section 6.4, bond dissociation energy. So this is now where we're getting into some of the why. Okay, we're going to use terms like thermodynamics and kinetics. Okay, we're introducing a lot of this terminology. Okay. And so let's look at homolysis again real quickly. I keep saying we're going to be done with this. We're using this as a teaching tool. Homolysis or homolytic cleavage means that the electrons, sorry, I show it that way, single fishhook arrows, the electrons are breaking. And so it's important for you to know that bond dissociation energy is the energy needed to homolytically cleave a covalent bond. Okay, that's by definition what it means. We're going to use those to help us these values to help us understand pyrolytic cleavage types of things. Again, I'm not going to ask you math problems on an exam, but it's worth doing the math problems to fully understand. Okay, this is where you have to make a judgment call. My general rule is do all the problems. Okay, do every single problem in the book, and you'll be more prepared. Okay. We use this term delta H with a little circle there. Superscript circle just means standard pressure and temperature. This equals bond dissociation energy. Okay. This is always positive, and that makes some sense because when delta H is positive, energy is absorbed and the reaction's endothermic. Okay, so what I mean by it's always positive, breaking in terms of breaking bonds. Okay, it's always positive in the sense that energy is released. Okay, to break a bond. to form a bond, it saves energy. Okay, and so anyway, don't worry about that too much. So the delta H can be positive or negative for reactions. Okay, because what we mean. Let me just step back. Okay, when I said always positive, I want to clarify that. Okay, bonds by definition have formed to save energy. So if you break them, you release energy. Okay, where it costs energy to break those bonds. Okay, whereas to form energy or to form bonds, it saves energy. Now the reality is in reactions we have some bonds forming and some bonds breaking. So delta H can be plus or minus. Okay. Overall. Okay, so let's look at, we use H2 as a nice example. Okay, let's look at what we mean by this. Delta H, when energy is absorbed, it's endothermic. Negative delta H, energy is released, exothermic. So let's look at H2 as a nice case study. You can have H with a bond, or you can have H to hydrogen atoms. So to form this is what I mean by to form a bond, delta H equals negative 104 kcals per mole. So every mole of this, you generate 100 kcals when these come together. That's the bond. That's when we form bonds. There's an energy saving reality. Okay, to break this bond costs energy. Okay. And what we mean by positive and negative is it takes 100 kcals per mole to break this bond. Okay. So that much energy is absorbed to break this bond apart. Okay, so some generalities: shorter bonds are stronger, generally speaking. So let's show a trend. CH3F. We're talking about the carbon halogen bond. Size of halogen, it's farther away from the carbon. Shorter bonds is going to be stronger, 109. I'm going to use kcals per mole to be consistent. And so the increasing delta H. So it's stronger bonds are shorter. Okay, shorter bonds are stronger. Okay, so let's look at reactions. A positive delta H means that starting material bonds are stronger than product bonds. I use SM and PD often. Okay. So plus delta H means the starting material bonds are stronger. And we're all talking about thermodynamics here, just for the record. Delta H means that product bonds, the negative delta H product bonds, stronger than starting material bonds. Look another example. CH3 tert-butyl chloride, what we call this, plus water. You can do a substitution. Okay, substitute chloride for OH, get an HCl as a byproduct. Again, in principle, this can go from right to left as well. Okay, so, but this one has a negative 3 kcals per mole delta H. And it's the delta H direction. So thermodynamically, it's favorable to go from left to right. Okay, we're going to find out that thermodynamics are not the only consideration. Okay, but what we do, we broke these two bonds, broken. We formed two bonds. So you can calculate these, do the calculations, go through some of these problems, understand what we mean. Some bonds are broken, some bonds are formed. Okay. Now, this tells us nothing about mechanism or rate. It tells us nothing about effect of solvent. Okay, keep in mind, all these numbers are for homolytic bond cleavage. They're not going to, it doesn't tell us definitively, okay, what will happen and what won't happen. Okay, that's a more complicated question. Now that leads us into 6.5 is thermodynamics and kinetics. These are the two factors that we need to consider for a reaction. Thermodynamics deals with energy levels of starting materials and products and equilibrium. Energy of starting materials and products and the equilibrium between those two things. Kinetics deals with reaction rates, how fast, activation energy. You'll see this term a lot. So we got a reaction, A plus B goes to C. Again, let's put this in equilibrium. In principle, everything's in equilibrium. We've shown this with acid-base chemistry. What is the KEQ? This is review from Gen Chem, concentration of products over concentration of reactants. Okay. If KEQ is greater than 1, products favored. KEQ less than 1, starting material favored. Okay, this is pKa. We went through this in the video before. pKa is just a KEQ minus water. It's sort of a specialized, it's a Ka value. We take the minus the log of that, get a pKa, it gives us a number. Okay, so not so different here. Now we're just talking about more complex reactions. So equilibrium is proportional to this value, delta G, and this determines starting materials products at equilibrium. Okay, so delta G equals the delta G of products minus the delta G of starting materials. It also equals minus the RT ln KEQ. Again, these are equations to relate the equilibrium constant to delta G. R is a constant. We've got temperature, etc. Okay. I'm just introducing you and reminding you of some of these things. You need to go work the problems. If KEQ is greater than 1, we have a negative delta G. Products are favored. Okay. Negative delta G over here. Okay. Positive delta G if it's less than 1. So work through some of those. Again, I highly recommend doing all the problems. Okay. 6.6 is another factor. We're going to talk about all these in organic terms. Okay, that's what I mean. I'm introducing some of these sort of Gen Chem mathematical principles that you should go through, and they're connected. But we're going to be talking about these in organic chemistry terms very quickly. So enthalpy and entropy. Delta G can be related to these two terms. Delta H we've introduced, minus T delta S. Okay, S is a change in disorder. It's randomness. It's chaos. T is temperature. Delta H is the bond dissociation energy. Both of these terms contribute to the delta G. Okay, entropy is somewhat hard to articulate, and it's somewhat negligible. Okay, it's small compared to delta H. So for our purposes, many times we will mention entropy at times, and there's cases where it does come into play. But essentially, we're going to treat delta G as proportional delta H. These delta H values that are technically for homolytic bond cleavage, we can use them to help us understand reactions. Okay, so products are favored when delta G is negative, exothermic reaction. Okay, products favored when delta H, i.e. delta G, negative, exothermic. Okay. Technically, there's exergonic and endergonic. We use exothermic and endothermic. Okay, we make approximations, just like the pKa. Starting material favored when delta H, delta G is positive, endothermic. And we're going to show graphs to illustrate this. So we'll use delta H a lot. Okay. So let's give a few examples, okay, of chairs. Okay, these aren't reactions, these are conformations. Talked about this a lot in chapter 4. Can't get away from chairs, unfortunately. Okay. Again, we're not explaining the why about aromatics, but we'll use them as substituents a lot. Okay, so this is an aromatic. It's called a phenyl. Okay, and what we see is the equilibrium lies to the right, the chair conformation. Like so. This is in the equatorial position. This is in the axial. Equatorial is favored. So there's two ways you can write this. 2.9 kcals per mole, which is a lot, and 0 kcals per mole. Okay. Or negative 2.9 to 0. It's the same thing. It's a relative energy difference. There's 3 kcals difference in energy between these two conformations. This one over here is much, much, much more stable. It costs 3 kcals to go from here to here. Not to say it's impossible, it means it costs energy to do so. Recall that we showed this with a methyl group, and we gave numerical values as to the ratio here. The methyl group, sorry, is equatorial over here. Axial on the right. And so there's 5 of these molecules for every 95 here, 0 to 1.8 kcals. Okay, so higher energy, less molecules. All right, so now let's talk about these energy diagrams, okay? This is a schematic representation of energy and reaction coordinates. So we're going to look at a general reaction, A and B. We're going to look at a substitution reaction. We'll look at these in more detail in chapter 7. So we've substituted C for A here. Okay? There's 4 explanations, four ways you could kind of explain this. The first one looks like this. One arrow comes in, displaces the A minus. We would call this concerted. This is an arrow pushing mechanism, and that's a substitution. The other, a little bit more sophisticated picture. Again, we're going to go into more detail in 7. Let's just go through these kind of quickly. You take the same reaction, but you describe it in terms of transition state theory. What that means is that, in a sense, there's a half a bond. We put brackets and we put a double dagger to indicate a transition state. Now we put partial minus. This is the transition. It's the highest energy point when the C is displacing the A. And this means these are partial bonds. Partially broken, partially formed. The third is simply an exercise to explain this. I'm not going to draw all these out. I'm not going to put all this text. But just I'll say it verbally. I'm not going to ask you for anything like this, obviously. We're redrawing the exact same reaction, so just kind of listen. What we're saying is C minus approaches AB. There's electron-electron repulsion between the electron clouds. They're repulsing each other, so there's an increase in energy. And then there's a maximum energy. That's the transition state where A and B is partially broken, B and C is partially formed. Never isolated this transition state. Then energy decreases as B and C is formed and as A is leaving. And then there's an energy minimum of the products that's reached. Okay. All of that verbosity is, we don't want to say that every time. That's why we use arrows. Okay. And then the fourth way is energy versus what we call reaction coordinate. Okay, this is a diagram. You must be able to draw these. Okay, some of them. There's two major factors. Again, thermo versus kinetic. Okay. Energy difference between starting materials and products. Delta H is thermodynamics. Kinetics is activation energy. It's the minimum energy required to break bonds in the starting material. Okay, so it's an activation energy. So we're going to keep looking at our general reaction. I'm going to give you 4 different examples of a single step reaction. So now we're focused on a concerted single step reaction. You can look at figure 6.4 for these 4 examples. Okay, we're going to change these 2 variables, these thermo and kinetic terms. So let's look at these 4 examples. Okay, we're going to use terms slow and fast, and we're going to use exothermic and endothermic. So let's look at slow. That means there's a large activation energy, E sub A. Slow and exo, negative delta H. Energy is on the y-axis. Reaction coordinate, that just means the coordinates of the reactants involved. Okay, what's happening? So we have exothermic means it's going to go downhill, so to speak, overall. A, B plus C minus. Same reaction. And if it's slow and it's got a large activation, again, this is all qualitative and relative to one another. What we mean by the delta H term is this. It's negative. Okay, the relative position of starting materials and products favors products. Okay, products are favored by energy. Now, just because products are favored doesn't mean a reaction will ever go. If the activation energy is too high, there's not enough energy to overcome the barrier. Okay, so this is a barrier. I'm going to do some examples in class to help you understand this. E sub A is the height of the energy barrier. You have to have enough energy to get over the barrier. So it doesn't matter how exothermic something is, you may never get there. Okay, this is what catalysts are used for and things like that. Okay. But now let's look at our second case. And this is fast. So a small EA and exothermic. Try to keep things consistent in terms of the heights of things. This is the same. It's still an exothermic reaction. These dashed lines just help us to connect things to be able to talk about it. Delta H is the same, right? And over here we said A minus and BC. We have products now, okay? So the same thing, starting material, products, but it's a much lower activation energy. Less energy is required to get over the barrier, okay? So now let's look at 2 endothermic reactions, case 3 and 4. Here we have slow, endo, so we're back to a larger energy barrier. And now it's endothermic, if positive. Okay, so the starting materials are favored, okay, based on thermodynamics, okay? But again, if there's enough energy, there's a lot of reasons why you can make an endothermic reaction go. Okay, we're trying to introduce concepts here, not answer all of our questions, okay? So if endothermic reactions never went, we wouldn't be here, okay? Endothermic reactions can go. There's just things that need to happen, okay? And entropy does come into play in that, etc. So don't think of it like, you know, like an endothermic can't happen. It just means that you need energy to push it towards the products. Okay, there can be an irreversibility to something like this. So if it's a large energy barrier, for example, if you get the energy to go over it, then once they're formed, they're sort of happy and they don't want to go back. Okay, that's kind of a simplistic way to mention it. So you have starting materials, and then you have products. Same idea. This is slow, large EA, and it's endothermic. Same idea. It's a lower barrier. Delta H, endothermic, small activation energy. Okay. So let's look at an energy diagram, 6.8. 6 is really an intro chapter, okay? There's not a lot of questions that are going to come directly from this. We're introducing these, and you'll have to draw these diagrams for real cases, okay, in chapter 7, for example. All right, 6.8, energy diagram for a two-step reaction, stepwise. Same reaction. Okay, but a very different explanation. What we mean is that it's possible for A and B to break apart to form B plus and then have C minus. So this is an intermediate. It's possible that A and B can break, and then this would happen fast. Okay, and so you have heterolytic bond cleavage of AB, complete cleavage, and then you have formation of CB. Okay, in some cases these can be isolated, okay, and observed and studied. Okay, so we're going to draw an energy diagram for step 1 and then step 2. So we're basically putting two steps together. Again, the book walks you through this nicely in section 6.8, and then I'm going to show you the whole thing put together. So we'll do the whole thing, but we'll do one step at a time. All right, so we have A and B plus C minus. Okay, the plus just means they're being added together. It's not a formal charge. And what did we say? We said that this can go to an intermediate. Okay. And each of these steps. So for step 1, there's a delta H. Step 1. And it is endothermic. There's also an activation energy. I'm going to have to draw my arrow kind of funny there. Okay, the top of the hill is the highest energy point. That's the activation energy for step 1. And we say this is a transition state for step 1. And the transition state is simply that point, the highest energy point when these bonds, when it takes energy to break bonds. So it's the highest energy point before complete bond breaking. Delta minus, delta plus, partial. It's the energy max. Okay. And then it goes downhill to a local minima, the intermediate, INT, right? And then it's a lower energy barrier in step 2, and this makes sense. If you have a carbocation, for example, it's electron deficient, C is going to come in here real quickly. So this is downhill. It's just a little bit of energy to do that. Transition state is there, partial minus, partial plus, transition state 2. Okay. So there's EA2, and then what do we have? The delta H of 2, exothermic, and then the overall delta H is also exothermic. So it's putting two steps together. Okay, we have this intermediate. So what's the slowest step? Step 1. And it's the highest, it's the most amount of energy necessary to make this reaction go. So let's talk briefly about kinetics. I know at first when you see this stuff, it's confusing. Stick with it. Okay, so 6.9 is kinetics. The principles here. This is the study of reaction rates. Okay, energy of activation we've talked about. larger EA, slower reaction, smaller EA, faster reaction. So if we increase the activation energy, we decrease rate. Okay. Now, qualitatively, you should be able to work through these things. To see a diagram, perhaps, and explain it. If we decrease activation energy, we increase rate. If we increase concentration, CONC is concentration. We'll see these explicitly. We'll go through some math problems. If we increase the concentration, we also increase the rate. We increase the amount of molecules in proximity. If we increase temperature, we increase the rate at which the molecules are moving around. We increase the rate of the reaction. Importantly, delta G, delta H, KEQ, right? These are all thermodynamic terms. They're not related to activation energy or rate. Now, I say that, we will talk about something called the Hammond postulate later on that attempts to bring these two together, but they are separate terms, okay? So a rate law, let me tell you about a rate law. Reveals relationship between concentration, starting material, and rate. So there are ways in which we sort of attempt to bridge them together. The rate law brings concentration of starting materials together, but it's not KEQ, okay? So in the Hammond postulate, we'll attempt to bring some things together. The rate equals K is a rate constant times the concentration of reactants. Constant. I am never going to talk about numbers on this. Again, you should be able to work through some of these problems, and they will help you. They'll help you understand this better. Concentration of starting materials. If K is large, it's fast. If K is small, it's slow. That makes sense. But we're going to keep it very qualitative. But we will talk about concentrations. So let's recall our case here of concerted versus stepwise. We mentioned concerted or stepwise formation of BC. Okay, so we got this reaction, AB plus C minus goes to A minus plus BC. We said it could be concerted, and as C comes in and attacks B, A can leave all in one shot. We talked about a transition state for that looks like this. We have partial negatives and delta double dagger. Double dagger is just for transition state. This is the transition state. You go from here to here. That's the highest energy species, okay? So the point being, we're introducing things in Chapter 7 now, okay? This is a concerted reaction. Both starting materials, both reactants, A and B and C minus, they're going to be real things here soon, are involved in the rate determining step, RDS. Very, very important, okay? Since there's only one step, it has to be the rate determining step. Okay, but we're going to see in the stepwise, we're going to talk about rate determining step a lot. Okay, so rate determining step. So therefore the rate equals K times the concentration of AB times the concentration of C minus. And there are potential exponents here. These are just one. Okay, there's lots of cases where things can be zero order or second order. We're not going to even begin to delve into that. For our purposes, each reactant will always be first order in itself, but together the reaction is second order, right? Because there's two of them. 1 plus 1 is 2. Second order rate law is the sum of the exponents, okay? Again, you're going to be confused and disoriented at the beginning of this, but we're setting the stage for chapter 7, and we'll talk about this a lot. Okay, so that's second order, and just so you hear a term, SN2. We're going to be talking about SN2, substitution nucleophilic second order. Bimolecular, that's another synonym for the 2. Let's look at the stepwise of that same reaction where we said you can break things into intermediates. That's the first step. This is the energy diagram that we talked about. Step 1 is here. You form the cation intermediate, and step 2 is C is attacking that. Okay, it's the energy. It's the 2-step energy diagram. We talked about this as an intermediate. What we mean here is that one of these steps is rate determining. Okay, so the rate determining step C is not involved in the first step. We said that was the high energy step. So what's the rate determining step? Step 1, formation of what we're going to see as carbocation, B+. Okay, so step 2 does not matter regarding the rate. Therefore, what's the rate? Equals K. K is always generic, concentration of AB. That's it. Think about that. If you increase the concentration of C-, it doesn't affect a first order reaction. This is a first order reaction. There's only one of them, first order reaction. Very, very important. Second order, first order. So kinetics and thermodynamics, very important. What happens if you double the concentration of C-? Nothing. What happens if you double the concentration of AB? You double the rate. In the concerted, if you double either, you're going to see that you're going to double the rate. All right? So first order, we're going to see a term called SN1, substitution nucleophilic first order, or unimolecular. Unimolecular. There's only one of these. One reactant that's involved. All right, finally, 6.10 has to do with catalysts. All I'm going to do is tell you a few things. What do catalysts do and what they do not? They speed up rate. Okay. They speed up the rate. They lower the energy barrier. Okay. By lowering the energy activation, kinetic term, they speed up the rate. Okay, so it's they interact with things in such a way that they lower the energy barrier, they allow reaction to happen. They bring two reactive things in proximity, for example, they speed up the rate, and then they undergo no net change. Right? They're neither consumed nor destroyed. A catalyst is catalytic. You'll need a little bit of it. Okay, you don't need one piece of that for every one reactant. You need a little bit because it does its thing over and over. Okay, so it can be recovered, for example. You need to understand this concept. If I give you energy diagram and say what would be the effect of a catalyst in this reaction, you need to understand that it lowers the energy barrier, it speeds up the rate, and it undergoes no net change. So you need to understand. I'm not going to make you list it. Got to understand the principle. Okay, they do not though affect. Catalysts affect kinetics. That's the big message. They do not affect thermodynamics. What are the thermodynamic terms? Delta H, delta G, KEQ. All right. So examples of catalysts are acids like H2SO4. Palladium metal can be a catalyst. Enzymes, biological catalysts. Okay. You don't need to know these and list them, but these are examples. Okay. 6.11 is a nice section about enzymes. Read that. Okay. For your knowledge, very interesting to see some discussion of enzyme substrate complexes, and it talks about the breaking down of lactose. Okay, and but that concludes chapter 6. Only one lecture for this chapter, and again, chapter 6 is really an intro chapter to set the stage for chapter 7 and 8 and beyond. Okay.